Thank you, everyone. Thanks to the organizers for letting us present our results in such a beautiful place. So I'm going to try and show you how we used the Shrek experiment, the big experiment that Bernard showed you, to try and resolve velocity fluctuations at the smallest scales of the flow, which are dissipative length scales or intervortex length scales. We'll see. This is the work of a group of researchers from France and abroad and technical staff, which we call the Shrek collaboration. So that's the way I signed this presentation. I'll first give you an introduction about the motivations, and then I'll show you the local sensors that we have used. Most of them are homemade. Then the flow characteristics, the flow configuration, and then the main results of the talk. And as you'll see, we will not use hot wires in helium-2 because they have a somewhat exotic behavior in helium-2. But I'll give you in the end a bit of explanation about that. So, about the motivations, in the current state of our knowledge in inertially driven turbulence, I insist, what we know is that injecting mechanical energy in helium-2, in superfluid, works pretty much the same as in helium-1. If you rotate a turbine, you'll observe that the same kinetic energy is injected in the flow with the same turbine at the same velocity, so nothing new. That's what Bernard showed with the Kp, so the drag coefficient of turbines. Now, if you put Eulerian sensors, such as pitot-tube, which Maurer and Tabling did, and later Salor and others, you can look at the power spectral density of the velocity as a function of the frequency or the wave vector here, and look at how the cascade happens. And once again, it happens the same way. It seems to happen the same way in helium-1 and helium-2. You observe a k to the minus 5/3 with the same amplitudes. So this is interpreted as the fact that in helium-2, the two components of helium-2, the normal and superfluid, are locked together by the mutual friction. But as you may know, the main ingredient in this locking mechanism is the vortex tangle that creates in turbulent flows. So at larger scales than the intervortex spacing, this mutual friction mechanism is expected to be very efficient. But once you reach small scales comparable with the intervortex spacing or below, what happens? And that's pretty much the question that we are asking. So I may confuse in this presentation delta, the intervortex spacing, and eta, the dissipative length scales, because we now know it has been shown experimentally that they scale pretty much the same. So don't be shocked. So now what we need to do is to resolve those dissipative length scales, which are very small in general. So here is the way we have tried to do that. To have, with a fixed resolution of the sensors, what we need is to have the largest dissipative length scale possible. So in order to obtain that, what I see is I want a large integral length scale, which is what you will obtain with a large vessel. Let's choose Shrek if we have it at hand. But you also want a small Reynolds number, or at least moderate. Otherwise, the distance between the integral length scale and the dissipative length scale will be too large, and we'll have too small dissipative length scales. So we chose a particular configuration of Schreck in which we don't rotate the turbines, as Bernard showed you, in opposite directions, but in the same direction. With that, so we call it co-rotation. And with that, as you'll see, you obtain something like a solid body rotation with some bulk turbulence near the walls. And we have put here in the equatorial plane some velocity sensors that are targeted towards the azimuthal velocity. So here you have two of them, two kinds of them. You have two hot wires. I won't speak about this guy which broke very early in the experiment. So I will speak about this hot wire, which is 4 centimeters away from the wall, and about this little sensors, which is 1 centimeter away from the wall, which is a cantilever. So now let's come to a bit of details about those sensors. So as I said, there is a cantilever. The principle is, so it's a micro-machined device. It's micro-machined on a silicon oxide wafer, and you have a 300 meters long beam here, at the tip of which you have a disk of 100 micron. And this disk will act as an obstacle in front of the flow. You have a drag that pushes the disk and bends the beam, and we are going to measure the bending of the beam using strain gauges, classical nichrome strain gauges that are put onto the beam here, micro-machined onto the beam. So typically the drag, if the flow here is turbulent around the disk, will be quadratic, the force will be quadratic, and we expect a quadratic response with regard to the velocity here. So this is the response, and as you see, we have something quadratic in the range of the velocities that we have explored in Schreck. So this works pretty much the same way in helium-1 and helium-2. So this will enable us to compare directly helium-1 and helium-2. So it's you'll see there is a resonance at something like a few hundred hertz. So below that you have a large frequency response. I'm not sure you will see the peak. So it was a good question. Huh? Not this one. This one is few kilohertz, so it's kilohertz, not few hundred hertz. We also have a homemade pitot-like device. So I don't have a photo, sorry, but the principle is as usual. You measure the difference between the stagnation pressure on the top cavity here and the static pressure on the bottom cavity using a membrane. This time the deflection of the membrane is measured with a capacitor bridge. And if you do this difference, you obtain the dynamic pressure. So again, it's the density times v squared. And you obtain this quadratic response again to the flow. And again, this kind of sensors has been celebrated by previous experiments and works the same way in helium-1 and helium-2. Now the third sensor, which is most common in turbulence studies and works it works the same way in helium-1. So we can use it as a reference. As usual, you have a thermometric material in the form of a wire that you over it, and you'll measure the efficiency of the cooling. For example, this is a calibration curve obtained by maintaining the temperature of the wire constant. And what you see is that you have to, you see a typical square root response with regard to the power. Those kind of sensors are much more sensitive than the others to small velocity fluctuations because of the form of the calibration curve. And they have a much larger frequency response, so we will use them as reference sensors in helium-1. In helium-2, something exotic happens at high frequency, so I'll not use them in the first part. I'll show you what happens in the end. So now about the flow. As I said, we are rotating the turbines in the same direction. So here, the top and bottom turbines are rotated in the same direction. And what we obtain is an almost solid body rotation, so a velocity that increases linearly as you go away from the center of the tank. And as you reach the external wall, here the velocity tends to saturate, and we expect that in this region we have some kind of bulk turbulence. This is not boundary layer turbulence, I insist, and this is where we have put our sensors. You also have, due to the dissymmetry of the turbines, a small vertical velocity, which is at most 4% of the azimuthal velocity. So we won't care too much about that. Now, if we want to put numbers on the expected dissipative length scale, we need to define a turbulence Reynolds number. So for that, we need the RMS of the velocity and the integral length scale. The RMS of the velocity, we obtain it through the turbulence intensity, which is about 5%. We measure it, as I said, with the hot wires. And the turbulence intensity here tends to be this number. At low velocity, we have noise that we must take into account to compute this in order to compute this number. But this is a quite low turbulence intensity, closer to grid turbulence than, for example, to jets or to what we obtain in counter-rotation in Shrek. Now the integral length scale, it is defined as the integral of the autocorrelation coefficient of the velocity. Experimentally, it's often hard to use that definition because, for example, long drift of the sensor signal may affect this integral. And we use a somewhat simplified definition. If you assume that you have an idealized Kolmogorov spectrum, so here you have a power spectral density of the velocity measured by the hot wire. If you assume that you have here a white noise at low frequency and followed by a typical power law k to the minus 5/3, at the intersection here you can define a wave vector k0, k0, that you can use to get the integral length scale, and here we obtain 3 centimeters. So with that big tank, we finally obtain a not so large integral length scale, unfortunately. But this number is quite robust and doesn't depend on the velocity, so we are happy with it. Now let's put numbers on the expected dissipative range of scales. We can calculate the turbulent Reynolds number, the VRMS times L divided by the kinematic viscosity of normal helium. And we obtain those numbers, which is a range of it ranges between 5 and 50 microns, which is bad news. This is much lower. It's a bit lower than the resolution of our sensors, which is between 100 and 500 microns. Fortunately, people have reported to see effects of the dissipation at higher scales than eta. For example, if we follow Midlarski and Warhaft, we could expect dissipative effect at scales as large as 100 times eta. So there is a hope, let's say, because in this case, our sensors should be able to resolve those near dissipative range of scale. Yeah. 30? Okay, this is the number I got from this paper. So, as I said, this is an example. This is not meant to be a truth. Just to give us hope. Now let's come to the results. So again, in Helium-1, we can compare our sensors to make sure they work well. This is a comparison at quite low velocity and high velocity of the hot wire signal. So as I said, it has a much larger dynamics sensitivity. But at low frequencies, the spectra of the pitot and the hot wire agree quite well until the pitot reaches its ground noise. Same for the higher velocity, so we are quite confident in our sensors. We could do the same comparison between the cantilever and the hot wire. It's not as good, but it's again quite good. And now let's come to the main result. It's Helmholtz. You mean this peak? It's Helmholtz resonance in the pitot. It's in general. It's what limits the temporal resolution of pitot. It's a mechanical resonance inside the tube because of the compressibility of the fluid. Okay, they say it's a membrane. Okay, so mechanical resonance of the membrane, but it's related to the volume of the. Okay, so bullshit. Sorry. So what we observe, if now we go to helium-2, so we decrease the temperature, is that from this green spectrum that we observed previously, which drops a bit harder here from this frequency, in helium-2, the energy tends to not decrease as fast. That's the most I can say when I see that. And actually, we don't have much more quantitative results than that. But in fact, this is what all the predictions, whoever do them, have predicted in helium-2. And we observe the very same behavior with the cantilever when at large scale the spectra agree, and at small scale, where in helium-1 the green curve the spectrum tends to drop, the energy in helium-2 is higher for the small scales. So this is it with this result. We don't have much more quantitative result, but it's quite motivating for the future. We have addressed this problem of trying to resolve the dissipative length scales or the smallest scales of the flow. The strategy was to use fixed resolution sensors of order 100 to 500 microns, the strategy was also to have a modest Reynolds number in a big tank. We have confirmed the usual results, which is that at large scale, nothing is different in helium-1 and helium-2. And we see more energy at high frequency in helium-2, which is compatible with the energy pileup that all models predict. Now, il me reste combien de temps? 10 minutes. Okay. Now I'll spend a bit of time telling you about what happens with the hot wires in helium-2. If I try to do the same comparison as I did previously in helium-1, so in helium-1 we had the hot wire here and the pitot tube here, so they start to disagree when the pitot reaches its ground noise. In helium-2 you have the pitot that has slightly more energy at large frequency, but what we see with the hot wire is a large, big bump. So first, we must insist on something, which is that this is not velocity fluctuation. Otherwise, the pitot would have the very same bump here. So what can it be? Let's look at this. If you increase the velocity, you'll see that the bump is displaced towards large frequencies and eventually becomes a simple departure from the original k to the -5 third law. So we have to define, if we want to study how it displaces, we have to define a frequency, which we defined as the inflection point here, so that the definition works whether we have a bump or a departure. And if we plot the frequency of the bump as a function of the velocity, here is what we see. So as we just saw, it increases with velocities as something that looks like a power law with an exponent between 1.5 and 2. If we change the configuration of the flow in order to have a stronger turbulence, so we push the flow in counter-rotation with a bit of dissymmetry to still have a mean flow, we see that the bump is displaced towards higher frequency again. So this bump seems to be sensitive to the strength, not only to the velocity, but the strength of the turbulence. And finally, we see that the frequency doesn't seem to depend on the temperature in helium-2. So now it's time to look at the signal itself, because we know that Fourier transform is not always the best tool to analyze things. What we see is that on the velocity signal here are superimposed peaks here. So this is the voltage of a hot wire driven in constant current. So you should see the voltage as an image of the temperature of the wire. So sometimes we see that the temperature of the wire drops rapidly and comes back. And we have events like this. And in fact, the bump in the Fourier space is a signature of, at the same time, the lifetime of those pulses, those glitches, and their time separation. So the idea to analyze this was to say, yeah, those may be objects flying at the advection velocity of the flow. And we could analyze those in terms of lengths, in separation length. So the translation is quite easy. Mean velocity divided by the f bump will give us some length. And we tried to analyze and guess what type of object we could be seeing. So I think I don't have time to detail this one, but we we have thought about some kind of Kármán streets that could develop due to the thermal pattern that develop around the wire in helium-2. Remember that we have counterflow, so there is quite exotic temperature profile around the wire, and there are structures that develop in the superfluid component and in normal component. And we were expecting that those could be unstable and lead to some kind of vortex structure shading, vortex shading. Well, this is this would lead to the right exponent, but it has defaults. The problem is that this is very temperature dependent, which it should not be, according to what we have seen. We are looking for something that doesn't depend on the temperature. And furthermore, we would not expect that the turbulence acts on this vortex shading as it does. It should simply enlarge the bump rather than changing the frequency of the bump. So this candidate has been eliminated. Then we thought about what if vortex pass on the wire. In the laminar situation, in solid body rotation, we would expect something like a vertical vortex array with a distance that depends on the inverse of the square root of the rotation frequency, giving rise to a frequency of the bump that would be in 1.5. So again, this exponent is compatible with what we want, but obviously there is no turbulence in that model. We cannot account for the variation due to the turbulent ratio. So finally, our best candidate to explain this is, as I said, is to look at vortex bundles in turbulent situations. What we know is that the intervortex distance behaves pretty much like eta, which is that it decreases with the Reynolds number at the 3/4. So if we compute the frequency that we would obtain on the tip of the hot wire, we find an exponent which is 7/4, so 1.75. And the good news is that frequency will depend on the turbulent intensity. So what do we obtain in the end? If we plot here not the frequency of the bump, but the obtained distance from the frequency of the bump as a function of the turbulence Reynolds number, then all the data collapse quite well onto a Reynolds to the minus 3/4 low. So this is encouraging for this line. This black line here is the low that I just showed you here, multiplied by 25. So looks like 25 times the intervortex distance. That's all I can say with what I have, and that will be my concluding remarks. So this hot wire is still not fully understood. We know that at small scales it acts even in the helium-2 as a standard hot wire, but at large scale we have those glitches that prevents us from using it as velocity sensor. The takeaway message is that the bump is not velocity fluctuations. It appears near the dissipative length scales, and it depends on the intensity of the turbulence, and scales pretty much like the intervortex spacing. That's it. Thank you.
We have time for one quick question, and then there will be more time for questions after the second talk.
So very likely, this turbulence is strongly polarized because of the propellers co-rotating.
Yeah.
So it would seem natural to ask whether essentially the vortex length in the z direction in the direction of the rotation is different to the vortex length in the transverse direction, which you could detect the ratio using second sound, a couple of second sound sensors this way and that way. Is that?
I did not get the end of the actual question at the end. What is it?
It would be interesting to essentially measure the ratio, measure the polarization of the average polarization of the vortices by monitoring second sound along and across.
It's hard. I think it would be hard because typical second sound tweezers need a mean velocity. You need something that brings the vortices inside the cavity. So if you put a second sound sensor in that direction with a flow that goes like this, you obtain something usable. But now if you want to know the asymmetry of the vortex line density, you'll have to orient the second sound sensor in direction that where it won't see the flow. So I guess it would be quite difficult. We could do that and that to discriminate two of the direction, but not that. If you with a horizontal velocity. But yeah, it's.
I guess there will be more time for questions after the second talk, or
okay.
do you want to keep going?
Okay.
Okay. So remember your questions. There will be more time after.
So I would like to present some work which has been done over the last 7 years by Jérôme Valentin, who is a clean room engineer. Eric Wallace was at that time a postdoc. And this is about a probe that we have named second sound tweezers. And basically the first initial motivation is the same as the one mentioned by Pantxo, that is to resolve what is happening at mesoscales in co-flow quantum turbulence. So we're now all convinced about this chronograph cascade, but what is happening between the end of the cascade, let's say, and the intervortex spacing. So the approach that has been described by Pantxo was to try to make probes which resolution is in this range. Now that's raise two delicate questions in practice. One is you need a probe that is sensitive to a few vortices, and so you need to understand what is the interaction between a small probe and a single vortex. And this is delicate because it involves pinning, it involves boundary layers, and this physics is not well known. So another approach, rather than trying to make a probe, rather than making a probe which is in this region, is to make a probe which is larger, but we will somehow integrate what is happening at smaller scale. And this is the path that we have followed. So to be more precise, let's take a tangle like that, and if you look at it at some scale, you can see these three sketches have the same polarization, the same average vorticity, but they have different vortex line density. So making the standard approach is to say if your probe has this resolution, it averages out all the things which are in the box. In this case, you get, for example, here the vorticity. But if you're able to measure what is smaller than the box, I mean the vortex line density, then you have some information on what is happening at smaller scales, typically dissipation, because if you have a vortex reconnection, then how fast are the wiggles damped is related to viscous dissipation, for example, reconnection process, scaling waves, etc. So the approach then is to to measure the local density of the vortex line. On Tuesday, I think Carlos said a word on second sound, answering a question in the audience. So I'm not going to go through this slide, but just to remind you, all we need for this talk is to recall that second sound is, you can see it as a temperature wave propagating in helium, liquid helium-2. And the velocity is about 20 meters per second. And you can, to produce a temperature wave, you can use a heater. And to detect it, you can use a thermometer. And if the heater and the thermometers are on some plates which are parallel, the temperature wave will reflex, and you can make some resonances. So you can make some resonant cavity for temperature wave. So this shows, for example, the first mode of resonance. But we can have higher modes. So this technique has been used for more than 50 years in the field. And what is interesting about this second sound is the fact that if you put on the acoustical path some vortex tangle, then the amplitude of the wave is damped. And the amount of damping is related to the amount of vortex line on the way. So those probes are used to measure how much vortex line density you have. What is original about our probes is that we try to make them very small and not invasive. So this is an idea. Give you an idea, this is a heating plate, thermometer plate. They are parallel. Here you can see them from another point of view, this way. So they are well parallel and thin. And the temperature wave is in this area. So basically, if I will show you later some experiment, if the wind tunnel size is typical is the room, for example, let's say, if you make in proportion, this system will be about this big. And the thickness of my end will be a heater, the other one will be a thermometer. The thickness of my end will be 1 millimeter or 2, and about 10 centimeters away. So it's really a local probe, and it's so thin that it is non-invasive. So as the field flies through the probe, we can measure in real time what is the amount of vortices or entropy. Yes, sure. Yes, and yes, and this is there's a lot of effect like that. Awake or behind, we wouldn't care. But you can have a boundary layer which develops, and you can have also, you can deflect some flow from the support, for example. So this effect, and the boundary layer condition sets the thickness of the plates. The thickness of the plates here is about 15 micron. To make sure, then we can estimate what is the boundary layer which develops. And we know that the second sound wave that we measure mostly measure what is happening in the central region, not on the plates. So this is how it's sized. In fact, all the design consideration, they are explained. I mean, nearly all the sizes that you see, this thickness, this length, the thickness here, etc., are detailed. The physics is detailed in the paper which is in press. And tricks like, you see, for example, there are notches like that. This is to make sure that the second sound is not bouncing back and forth between the legs. And you can see a hole here. This is to make a precise alignment. We put some joystick, we align the plates, and then so to understand what is going on, we have developed a model which accounts for diffraction, near-field diffraction, and advection. And I'm not going to go through the model, but it's basically optical interferometric model. And we can predict, for example, what is the temperature field here for the fifth mode of resonance between a heating plate, thermometer plate. And you can also predict what is the spectrum, the frequency, the resonance spectrum. And we can compare it to experiments. As you can see, what we measure with the tweezer and what the numerics based on the model are doing, with one adjustable parameter, we get the whole picture. So we are quite happy with understanding of how it works. This is, for example, the fact that the first mode of resonance. So, sorry, I did not explain this curve. This is basically the frequency of a temperature wave, and this is the magnitude of well, you see, it's more the magnitude of a temperature wave. And this is the first mode of resonance, second, third, etc., etc. So all this effect, and okay, I can go through that if you want, but this is just to give you an idea that we understand what is going on, and in the so when the usual way second sound probes are used. Oh, and if you want to see probes and how they are made, I can show you some silicon wafer from which they are made of. So this is a typical silicon wafer, and you can see all these holes corresponds to one element of the probes. And I have some other stuff for those interested. And so if you have a tangle, you get some attenuation, but you can also get some attenuation if you have a flow which pushes away the second sound. So this ballistic advection produces some apparent damping, but there's a fundamental difference between the two is this one increases the acoustical path. So it changes the phase, so we can discriminate between both effects. And this is a new result, and we show that by adjusting geometrical parameters of these tweezers, we can make some which are more selectively measure vortices, vortex line, and some which measure velocity. Quickly, there's another way to measure with the single tweezers both vorticity and velocity. But I'm not going. I can answer a question on that. That's a slide remark, a side remark. I'm not going to go through this one, but this is to we have introduced 3 new mathematical processing methods to convert the measured signal into either velocity or vortex line density. They are also presented in this paper, and they basically, they allow to separate, to distinguish the bulk attenuation and velocity related attenuation in the complex plane using the phase information of the signal. Now I'm going to finish showing you some an example of how we use this probe in real life in one experiment. It's a wind tunnel, superfluid wind tunnel. We have a grid, upflow. This is about 8 centimeters. And you have 3 second sound tweezers here, and 1 pitot tube, or stagnation pressure anemometer. And for example, you can see here pointing, the flow is coming from the top to the bottom. You can see the 2 plates facing each other. And upflow, at some distance, there's a grid. So we are in the near wake of the grid here. And I'm only going to show you one single statistics on this experiment, but in this paper we have also spectrum. This is showing you behind the grid in a different superfluid temperature, which are here, which corresponds to superfluid fraction from 16 to 80%. We have the velocity statistics measured by the second sound tweezer is nearly Gaussian, as expected, and the velocity statistics of a vortex line density, or could call that the superfluid entropy, something like that, is highly non-Gaussian, and this is what it is reminiscent of what people see in classical turbulence when they look at entropy or absolute value of vorticity or vorticity itself. Okay, and this is my last slide, which summarizes findings. So we have shown that these second sound tweezers can measure either vorticity or velocity. We have introduced some new processing method in the complex plane which eliminates mathematically the out-of-phase signal, which allows to really measure what we want, only velocity, only vorticity. And regarding the findings, I didn't show the spectra, but regarding the PDF of a fluctuation of a vortex line density, we have this strong asymmetry, which is independent of the superfluid fraction, and which suggests that this superfluid, with a superfluid experiment, well, it suggests that we have a continuity to the Navier-Stokes Navier-Stokes turbulence. So we don't know what is the corresponding quantity in classical turbulence of vortex line density. Is it entropy? Is it the square root of entropy? Is it the absolute value of vorticity? Is it what is it? But if okay, it's open. It opens. This opens a door, I think. Okay, thank you.
Okay, thank you very much. So now we have time for questions for both talks.
So thanks, Philippe. I have two questions. The first one: have you looked at the log of the vortex length, the PDF of the log of the total vortex length? So somehow you will expect this, as you say, related to entropy, and maybe it's log normal. It will be kind of natural to look at it.
When you say the log, you mean not this is a log already?
No.
No. Okay, no, I don't know.
I don't know. So this it might be if it's related to dissipation. And the other one is related to the identification of the intervortex distance with eta. Mm-hmm. So we have been over there maybe last 2 years with Nico and Juan comparing Navier-Stokes and GP. Mm-hmm. And what we realized that actually we need to use the Taylor microscale and compare that scale with the intervortex distance in order to compare simulations. Okay.
So this is more related to a Pantxo talk, eta viscous.
Yeah. So, but you also use it to mention it, and which is good for the experiment, meaning that if eta will be too small to measure it, okay, Taylor microscale, maybe you could go a bit below and look at the quantum effects. So this is something that Mark and Caroline actually realized in their first paper, and so I don't know if I really understand the Taylor microscale, apart from its mathematical definition. But what you would expect maybe that eta in Navier-Stokes is kind of the size of vortex tube, okay? And lambda is more or less where turbulence stops being Kolmogorov, okay? So that intuitively it's, I will say, okay, the cascade stops at the intervortex distance, okay? Morally speaking, this should be the Taylor microscale, whereas you still have physics between that and eta, which is the smallest one. So it's just a comment, okay, that it's actually good for the experiment, because it means that it's maybe easier to look at the quantum effects.
I think when you look at experiments, well, usually we try to make the smallest process possible. So, well, if in the kind of physics we are doing. But I think the first small dimension of the system that we hit is the length scale at which superfluid and amorphic are no longer coupled. This comes before the viscous scale and before the intervortex spacing. So it's another scale which is proportional to the intervortex spacing, much bigger. No, it's not a Taylor scale. Well, it's. It's not the Taylor scale because it's related to the coupling between the two. It's a temperature-dependent scale.
Meneguzzi and Vincent, that the Taylor length was the length, typical length of the vortices. I don't know. It's some remembrance from 1990s. You don't think so, Marc-Etienne? You remember that's what they told in their paper. Oh, okay.
Yeah.
From what I read in classical turbulence, the Taylor scale is typically if you look at I think a velocity signal or velocity signal, it's a typical distance between the zeros that you get from this velocity signal, and this maybe somehow is related to some kind of distance between vortices in quantum turbulence, but it's not very clear. But maybe there is a connection in I don't know that way.
Just a small comment. Another physical interpretation of the Taylor scale, even classic turbulence, it's the average travel distance of an eddy over a Kolmogorov turnover time scale. So if you ask how much does it travel being advected by the RMS during a Kolmogorov time scale, that's the Taylor scale. So very often it's hard to physically interpret the Taylor scale. That's an interpretation which might be relevant here because you're talking about sort of the travel distance of these. Yeah, maybe. Yeah. Then it would be the travel distance, maybe. Yeah, possibly.
What is the typical resolution in terms of vortex lines per square centimeter compared to old-fashioned second sound receivers, you know, embedded in the walls, which are large?
The sensitivity in the smallest intervortex, the largest intervortex distance that we can see with those probes is not as good as with a microscopic probe. The reason is not that we cannot do it. We could do it by changing the aspect ratio of the probe, but we have to make a compromise. If we have a too good resolution, that means the quality factor is large, and that means the time resolution is poor. So we always end up making a compromise between the mean velocity of the flow, the size of the probe, and the time resolution that we want, and that sets the definition, the resolution. So it's a compromise depending on.
I have a quick question. How do you do calibration? How do you calibrate the line density?
So we assume that the standard knowledge about our second sound is dissipated by a vortex line is valid. We assume that also locally we are isotropic to convert or the temperature calibration. What calibration of what?
Absolute line density. I mean, for instance, can you install it in rotation cryostate and then?
We could install it, but this probe is designed, what I've shown, for a mean flow, which is parallel to the plate. If we could put it in a rotating cryostat, probably it would work. But if you put it in a rotating cryostat with some transverse velocity, it won't work.
No, I mean, if you generate solid body rotation and put this plate in parallel with the array direction.
Well, and the probe is turning with the cryostat or not? If the probe is not turning with the cryostat, it will not work. If the probe is turning with the cryostat, it will work.
Yeah, I have a question to Pantxo. When you showed your heat velocity signal, and you were saying what is striking is some puff of heat, but I rather thought that what is striking is the anti-puff of things. Is that you had some constant level, and then suddenly you had a drop of heat.
Yeah.
So is it more compatible with the von Karman picture or not?
No, the problem with the von Karman picture, if I may.
Or if not, what is the interpretation of this anti-drop, of these drops?
The drops are, as I said, you can imagine them as drops of the temperature. So it means that suddenly the hot wire is very well cooled down. And I suppose you were talking about this. So the bump is in fact a signature of those intense cooling events, and in fact a signature of their distance and more or less a bit also of the lifetime of those pulses.
Okay, so the bumps are generated by things that advect very quickly temperature.
Either advected or detached at the mean velocity of the fluid.
Thank you. I have two questions about that. First, how is the hot wire driven? I mean, is it driven at a constant temperature,
Depends.
constant heat flux, or what?
So for most of the result I've shown you before, it was constant temperature.
Yes.
Which is the most common way of driving a hot wire. Here it was in constant current.
Okay.
It's easier for showing, and it was also easier to drive this one in constant current for technical reasons.
All right. And I had another question, I mean, which is rather related to the other type of sensor, a thing like that to measure second sound. You mentioned spectrum. How do they look like? You didn't show them.
No, I didn't show them. I have prepared the slides. It's not this one, but
they look like that. So this is a velocity spectrum. It's not brighter because we are in the near field of the grid. So the turbulence cascade is not completely developed yet. So we expect it to go. This is according to the literature. That's what we expected. The turbulence intensity is about 10%. And this is the spectrum of vortex line density, or I would call it superfluid entropy, but I know you don't like the term. Yeah, this is that. They have this rounded shape. When you look at where we have this inertial range here, it's really rounded. It does not depend on temperature, which is surprising. We didn't expect it. But we are quite confident in the validity. Well, we hand here because this is a limit of the resolution, but we trust them till there. So we don't really understand that. But
what does it mean that it doesn't depend on temperature physically? I mean, it's very strange, no?
I don't know. It was the biggest surprise for me. Yeah, I don't know. I expected naively that at small scale, when you dictate the temperature, you have more and more extra lines which are produced, and you should see them. If these lines are produced very uniformly, we don't see it because we uniform, we don't contribute to the spectrum. But I expect them to appear in patching. So I don't know. But I really don't know. And the fact that it's founded is probably because it's a mixing of inertial range physics with what is happening at small scale. So probably the Power law is broken because we are mixing information from it. So this is not really surprising. But the temperature dependence is really surprising.
Further questions?
Yeah. This is just for time to show it, but it's a result we done with Patrick Sankara, and he came to Grenoble to make the measurement. And he was a PhD student at the time of Marco Lancia. And we've been moving. So this is to show you that we can use this probe just to map the vorticity field in a jet. So we have a measure of vorticity field in a jet, and we could fit them with entropy fit in a jet, and we could have a fit for the entropy for the result. It's also published.
How does it compare with the classical entropy of the same jet?
We don't find any literature on that. So we kind of made some end model based on classical turbulence, and it works. But well, it works. We have to believe it. Marco does not believe in it, but Patrick and myself believe in it. So in the paper we say we have one model from Patrick and myself, and one model from ours.
Okay. Any further? And like a last one about the heated wire. Does it generate a vorticity on its own just by the heat flux from the wire?
Yeah, sure.
Do you have any estimation of how does that tangle close to the wire looks like?
I have an estimate vorticity profile with lengths. It's at the end of the. I think I had no time to show you that, but You have here the temperature profile around the wire, and here the expected vorticity profile if you believe in classical counterflow literature. So you don't have numbers here, but this is much, much larger than the vortex line density in the flow. And you'll reach the vortex line density of the flow at distances of about a few diameters of the. So you have a very dense vortex line just around the wire, and a few diameters away, you're done with them.
And the wire is heated all the way to helium 1 regime. It's overheated.
In fact,
outside of.
Yeah, this is what ensures the sensitivity to the velocity, as we showed. So, in fact, the fact that those wires are sensitive to velocity is due to this thin helium-1 layer on the wire. But the initial reason why we chose to overheat it very high, 20 Kelvin, is because the material, platinum rhodium, is not sensitive below the temperature. So you would have no signal from the material itself. There is no more resistance variation below, let's say, 10 Kelvin.
So there's a vapor bubble around it.
No, there's no bubble because we have, as Bernard said, a pressure which is higher than the pressure than the critical pressure.
Okay.
So we don't have a bubble. We have a strong density variation in this region, but no gas to liquid transition.
And the last question, and then we'll continue during the coffee break.
Thanks a lot for the nice talks. So from here, you can, I would say if I look at the profile of the vortex line density, you could in some sense define a boundary layer, right? So the distance.
That's what we did. In fact, this is, we found a way to define some kind of.
So is it possible? Have you looked at the dependence of the thickness of this boundary layer as a function of the flow conditions, the temperature of the bath? If so, do you have? Is there?
You mean the width of this peak?
Yeah.
For example, I would not expect that it as a function of the velocity. You say?
Yeah.
I would not expect that this varies much because the sensitivity to velocity, so the heat flux that we have to push inside the fluid in order to maintain this temperature is mainly what fixes this peak, the width of this peak, and the absolute value of this flux varies very poorly with the velocity. It varies, so we can do something with it, but very poorly. It's, let's say, keeps almost constant as a function of the velocity. So I don't expect that to vary.
Okay, let's thank the speakers again and continue.